Now let's look at how we can implement interrupts on our processor. Okay, so what I've got set up here is a very simple program with a couple of extra pieces in here. So I've got two functions that I've already got defined. The first one is setup LED1, and all this does is make sure we turn on and enable GPIO for the LED. So this is a very simple blink program, and the idea is that when I press the button, it's going to trigger, when I press switch 1, it's going to trigger an interrupt, and that interrupt is going to run a handler function that's going to toggle the LED. So it's like hello world for interrupts, right? And this will tell us how we need to set up this particular device and get it all up and running. And using it, we'll learn a lot about how interrupts are used on this processor. I've got a to-do for my button interrupt handler set here, so this is where I'll define that. And then I've got set up switch 1 as an interrupt. And I've already got some pieces filled in, and basically what these are enables for the port C clock, so that allows me to take input off of port C. I set up the port C pin 3, that is the switch 1 pin, as GPIO. So this is GPIO, but I can also configure it as an interrupt, and we'll look at how to do that. And I've set it up as input, so we can read from it from software. We don't actually need that part, as we'll see here in a second. Then the other parts of setting up this switch 1 as an interrupt trigger is setting the priority, which in this case we'll leave as 0, and we'll need to call the core API in order to enable interrupt requests for this particular source. Then my main down here is something just really simple. I call my hardware init function to wake everything up, then set up LED1 and set up that switch interrupt, and then it goes into a busy loop. So we can put anything we want here, and because I've set up this interrupt once, the handler will get called anytime we press the button. I don't actually have to tell it to call that function explicitly. So the first thing I'm going to do is in the switch 1 interrupt function, I'm going to think about my priorities for this particular interrupt source. In the Freedom board, or actually in the KL46Z, the interrupt priorities, the interrupt urgency is communicated by a lower priority number. So 0 is the most urgent that a regular interrupt can be, and we have several interrupt levels. 4 is the maximum or is the least urgent interrupt source. So we have several interrupt priority levels, 0 being most urgent and 4 being least urgent, and the system interrupts are even negative ones. These are ones that can't be preempted by any user code. So if there's a system halt, I can't interrupt a system halt with something else, something like that, right? So 0 is the highest priority that we can manage. I'm going to leave it as priority 0. If I were to modify the priority, there's a specific register in the NVIC. The NVIC has more documentation. So if we switch over to the reference manual, and to find the NVIC information, I'm just going to go Control F, NVIC. It's not that one. There it is. In the core modules section. And there's a whole bunch of detail here. The first one is interrupt priority levels. So there is an NVIC IPR register for every single peripheral that can generate an interrupt. And I can write 2 bits, that's 4 levels of priority, into these registers, and that will give me control over the priority of that interrupt source. I'm going to leave ours 0. The next thing is to enable this interrupt request source. The function that I need to call is the NVIC enable IRQ function, and it takes one argument, and that is the interrupt request number. Now, where do I find that number? I'm going to put a number right in here as a placeholder, but the number of the interrupt request is in that same area on the it's in chapter 3, NVIC description inside of our reference manual. And if we scroll down a whole bunch, we find the interrupt vector assignment. So this is defined by hardware, and this is the vector of functions that we can associate with specific interrupt request numbers. And when that interrupt request is completed, or when that interrupt request signal comes in, a particular function that we associate in this table executes. So this, you can see this table starts at the very beginning of memory, at the very lowest parts of memory, and it goes up by 4 bytes each. So it's a 32-bit system. Every pointer in the system is 32 bits, so it goes up by 4 bytes with every single slot in the table, and of a function pointer. The name of a function is just a function pointer to a piece of code in memory, and that's what we store in each one of these slots. We can see that what we start off was the ARM core system handler vectors, and these are functions that we can associate with specific ARM core events, like a hard fault, or a non-maskable interrupt, or supervisor calls, or system ticks, and all kinds of stuff like that. And you'll notice that they don't have interrupt request numbers because they're non-maskable. It means that we can't actually hide them. We can't turn them off. Only interrupt request signals that are maskable have a number, and those are the ones that are kind of like user-defined ones. These are ones that are built into hardware, so we can't ever actually turn them off. So our interrupt request numbers are listed in the next column, and you can see that it's the same number as the interrupt vector table entry number plus minus 16 in this case, right? So here we've got a bunch of different sources. The one that I'm looking for is on port C, which is here. So it's pin detect, port C, and port D. So interrupt source number 31 is the one that I want to enable to trigger on port C. So I'm just going to drop that number right in there, right? There's one more thing that we need to do inside of the setup switch 1 interrupt function, and that is to make sure that the port C PCR3 register is generating interrupts. And the way that I do that is by modifying some bits inside of this register. Looking at the port PCR register description, we see the IRQ region here, and if we click on that, it takes us to interrupt configuration. And basically what this says is this GPIO pin will trigger an interrupt on whatever the set condition is. There's some DMA conditions. We can set it on levels, so whenever this particular signal is logic 0, it triggers an interrupt. We got different edge conditions, or when it's logic 1, it triggers an interrupt. This is an active low switch, so the button goes low when it's pressed. So we're going to go with 1010, which is interrupt on falling edge. And this is at bit 16 of the PCR register. So I've already got that here. I've already got the PCR register here, and I'm going to modify my settings. So we're going to clear it first. Bit 16 starts at F0, so there's 2 bytes, and then F, so I'm clearing those 4 bits. And I'm going to do the same thing here as a mask, and I need to set hex A 16 bits in as part of that, and that enables interrupts on falling edge. And that's all I need to do to enable interrupts for this source. The other side is that I need to enable, I need to associate a function, a handler, with this interrupt source. And the way that I do that is I need to look up what the interrupt vector name is. And the way where I find that information is in the project settings. I go to startup code, and there is a little assembly file called startup mkl46z4.s. And in here, this is what it starts off with, is a description of the interrupt service vector and all of the entries that are defined for it. So we can see there's the DMA IRQ handler, there's a TPM IRQ handler, stuff like this. And what these are is named locations in memory that are unassociated, right? So basically it's a mapping. If I define a function that has this same name, the pointer to that function is going to be placed inside this location in memory. So it's a really handy little thing here, and they've done a lot of great work for us to make this really easy. So all I have to do is copy this name, and then I can define my interrupt handler here. And this is a function name, so it's got to give a void return type. Interrupts never return anything. There's nothing to return to, and they can't take any parameters because they're never actually called by normal source code, so we can't pass anything into them. So that defines my interrupt handler. That's all I need to do there. Now I can define what needs to happen inside the interrupt. In this case, I'm just toggling the LED pin, which we know from class is GPIO-D, PTOR, 1 shifted 5. So that turns it on and off. So now my interrupt handler is complete. We've done everything that we need to set up interrupt handling in this particular processor. I've set a breakpoint next to the toggle so we can see when it toggles, and I can go ahead and debug this. All right, let's make sure all of the signals our setup steps run perfectly without having any scary issues. Just step over these. Looks great. We're in the infinite loop, and I hit resume, and it's off and running. Fantastic. Now, let's see what happens when I press the switch. I trigger the interrupt. I press the switch, and it jumps straight to the toggle bits here. If I step over, it turns off, and that's fantastic. And let's see where it goes after this is done. It returns back, and we're back inside of infinite loop. Super cool. Trigger it again. And there we are, running right away, right? So let's resume. I hit it again, I hit it again. Uh-oh, something's happened. I'm stuck in the interrupt. Let's look at what's going on here. So back in the port PCR description, we see another ISF flag, and this is the interrupt service flag. And what this is a interrupt status flag. And what this is the bit that's set when this particular interrupt triggers. And this is also the bit that controls whether or not the interrupt is initiated and that service function runs. Now the thing is, as long as this is 1, it's going to keep triggering the interrupt request. And that's what we saw before. As soon as we set it once, it keeps, as soon as we're set it once by pressing the button, it keeps triggering, and it triggers forever. Now what we need to do is, we saw up here, there's a W1C. That means write 1 to clear. So what we need to do inside of the interrupt handler is to write a 1 to that bit and make sure that it's clear so that the interrupt only occurs once for every push of the button. To do that, we're going to write to the port C PCR 3 bits at location 24. That's the ISF flag bit. That clears the interrupt flag, and the next instruction toggles the bit, and we do whatever. So always in the interrupt handler, you want to clear the interrupt flag unless you always want it to run forever. So executing in debug mode again, I hit resume, and it's off and running. My LED is on. I press the button. It jumps right into the interrupt handler, triggers right there. I step over, it turns the LED off. I hit resume again. It's off and running. I hit the button, it triggers once again. Step over, that looks great. I'm going to take the breakpoint off and let it fly. And now every time I hit the button, the LED turns on and off. And this is all happening in the interrupt service routine. So it's happening outside of main. It's all happening in the background. It's background behavior. And this is a really powerful tool for designing embedded systems that can handle events that occur anytime. And it's really, really powerful. So apply it with great responsibility.